In the last video, we looked at how these DC to DC converters work, and now it's time to design them. While I showed these boards a bit last time, I never revealed their secret ability, which is enabled by this small 10-pin connector up here. To keep this video exciting and not just me reading off a load of theory and equations like most design videos, I've made the converter breakout board, which allows us to view what's going on inside the converter. So every equation I show and waveform I describe, we're going to take a look at on real converters. I've also written a bit of code that uses a pair of power monitor modules to track input and output voltage and current, which I've used for some nice graphs we're going to be looking at shortly. Big thanks to Telonic for letting me borrow this excellent Kikasui electronic load, which lets us easily see how the waveforms of the converter change at different loads. As you can see, this is quite a long video, so I'm going to quickly run through the things we'll be looking at just in case you're in a rush and just want to skip to whichever bit's relevant to you. We're going to start by taking a look at the standard equations for the output voltages of these three topologies, as these tell us the duty cycle we'll need to run at, which dictates a lot of our design decisions later on. After that, we'll get into the main part of the design, calculating our component values. While I'll mostly be focusing on the buck converter, the concepts are exactly the same for boost and buck boost, as well as many other power converter topologies. Next, I'll cover the key parameters to look at when selecting components, and we'll also take a quick look at a few key points regarding the layout and overall physical design of the converter, as this can make a huge difference to efficiency, reliability, EMI, basically everything. Then finally, we're going to check out how well these converters I've made perform, and whether they meet their specifications, including looking at how to analyse the losses in a specific component. If you're watching this video because you want to make your own DC to DC converter, get your PCBs for it from as little as £1.50 from JLCPCB. Simply drag and drop your Gerber files onto their website to see the automatically calculated price for your board, as well as an estimate for the mind-bogglingly low shipping cost. JLCPCB have some great options for power electronics, like 2-ounce inner and outer layers to increase current handling capability, and aluminium core PCBs for even more demanding applications. The converters I've made for this video use 4-layer PCBs, which makes routing connections between components much easier, and is something I strongly recommend, especially with JLCPCB's excellent multi-layer board prices. And now, let's take a look at the output voltage equations for the three converters. Now, absolutely everything I show today is going to be running at a 10V input, just to keep things consistent and the maths fairly simple. So here are the output voltage curves for all three topologies with respect to duty cycle. We can see how with these three converters, we cover every possible output voltage, with the buck converter to reduce voltage, the boost to increase, and the buck boost to invert. Now there's a few important things to note about these equations, so let's start by taking a closer look at the simplest, the buck converter. As we can see, the output voltage of an ideal buck converter has a perfect linear relationship with duty cycle, double the duty cycle, double the output voltage. But how true is this in reality? Well, here's the curve for the buck converter I've made, running with a constant output current of 1 amp. We can see it's fairly close, with a bigger discrepancy at lower duty cycles. This is because the voltage drop across our diode is much larger than it is across our MOSFET, and the lower the duty cycle, the more time we spend conducting through our diode, and less time through our more efficient MOSFET. This is one reason why a synchronous converter, using two MOSFETs, has better open-loop regulation, as the voltage drop is better matched between the two switches, so varies less with duty cycle. Now what I'm going to do is half the output current, and let's see how that affects the output voltage. Oh, what's going on? What's happened here is that between about 20% and 80% duty cycle, our inductor current is becoming discontinuous, meaning it's dropping to 0 when connected to our output in the second step. This happens at light load conditions when the output current is so low that not all the energy in the inductor actually gets to the load. As it still has to go somewhere, it instead charges up the output capacitor, causing the voltage to increase beyond what we'd expect given continuous current. This effect gets more extreme as we further reduce our output current, as we can see from this curve showing an output current of 100 mA. The kinks in the curve at 10 and 90% duty cycle are due to the shit function generator I used for these tests, so apologies for that. Now let's take a look at the curves for the other two topologies, starting with boost. Here's the ideal output voltage curve for a boost converter, and we can immediately see a bit of a problem. There's a limit to how high our duty cycle can be taken without causing damage to the converter from excessive output voltage. Usually we'll need to limit this to the voltage rating of the output capacitors, in this case 35 volts. But anyway, let's take a look at the real-world output voltage curve, this time at an output current of half an amp. And we can see that once again it follows the ideal curve pretty closely, with an almost constant half-volt drop. This drop is the forward voltage of the output diode, which all current at the output must pass through. As with the buck converter, we can reduce this voltage drop by swapping the diode with another active switch. Now let's reduce our output current so we once again enter discontinuous current mode, or DCM. At 100 mA we see somewhat similar behaviour to the buck converter. The difference, however, is that the output voltage isn't limited to the input voltage, it'll just keep on climbing. This becomes more apparent when we reduce our output current by a further factor of 5 down to 20 mA. Now at just 20% duty cycle, which we'd expect to give us a little over 12 volts, we're already at the maximum allowable output voltage of 35. Overall, this means discontinuous current in a boost converter is usually avoided, as it significantly increases the likelihood of overvoltage at the output. Another important takeaway is that at zero output current, so with nothing connected, even very low duty cycles have the ability to charge the output caps to very high voltages, which can damage anything connected to the output, including people. Finally, we're going to take a look at buck boost, which, as we can see, behaves almost identically to boost, except the curves start at 0 volts rather than at the input voltage. For clarity, I've inverted the output voltages to make them positive. Remember, a buck boost converter's output voltage is normally negative relative to the input. Before we move on, let's quickly take a look at how the output voltage changes as we vary the output current when the duty cycle is fixed, as I think this shows the effect of discontinuous current very clearly. First off, let's head back to the buck converter, where I varied the output current from 0 to 8 amps at duty cycles of 20, 50 and 100%. These are the output voltages we'd expect from an ideal converter, always operating in continuous current mode, and these are the output voltages we see in the real world. As we can see, the voltage drops more and more as we increase the current and get more losses in every component. At the other end, we can very clearly see when the inductor current becomes discontinuous and the output voltage shoots up. This of course doesn't happen at 100% duty cycle, as the inductor is always connected to the input, so there's never any opportunity for it to run out of energy. Here's the same for the boost converter at 0, 20 and 50% duty cycles. Again, we see the output voltage shooting up at around 200 mA. Interestingly, with the boost converter, we can see that at higher duty cycles we get more voltage drop. This is because the current through the input components, so the MOSFET and the inductor, increase not only with the output current but also the output voltage, just because the overall power is increasing. The reason the 50% duty cycle curve stops at just 4.5 amps is that, unsurprisingly, this boost converter designed for about 30 watts got quite hot when it was running at 100 watts. Finally, here's buck boost. Again, pretty much the same as boost except much less efficient, so we see more voltage drop and lower maximum currents. Now it's time to get into the actual design, starting by calculating the values required for the 3 energy storage elements, the input and output capacitors and the inductor. The inductance we need is determined by the maximum current ripple we can accept, which is a function of the voltage we apply at our switches, whereas the capacitance is determined by the voltage ripple, which is partly a result of the inductor's current ripple, hence why we need to calculate that first. To keep things simple, we're going to be making quite a few assumptions as we go along, such as ideal components and therefore a 100% efficiency. If we want more accurate calculations, we can always go back and refine our numbers later on. So first off, we have our inductor, and what we're going to do is rearrange the standard equation for inductor voltage, V equals L didt, to get inductance equals the integral of the voltage across the inductor, or the voltage time product, divided by the peak-to-peak current ripple. Now while this may sound rather complicated, it's actually very simple in practice because the waveforms we're dealing with are so simple. So let's take a look at them. Now first off, this is the PWM signal, so this comes from our controller and basically tells our MOSFET when to turn on and off. When it's high, the MOSFET's on, and when it's low, the MOSFET's off. You can see at the bottom of the screen I've got frequency and duty cycle measurements, and in this setup I can very easily vary the duty cycle, like this. But what we're interested in at the moment is the inductor, so let's have a look at the voltage across the inductor. There we go. You can see that when the MOSFET turns on, we put a positive voltage across our inductor, and then when the MOSFET turns off, there's a negative voltage across our inductor. Now I mentioned the integral of the voltage, or the voltage time product. That's essentially the area underneath this yellow curve. So we can either use this top one or this bottom one. The area will always be equal, even if we adjust the duty cycle. So you can see if I turn down the duty cycle, this bottom one gets wider but less tall, whereas this one is taller and narrower, so the area will be the same. Now while on the scope we can see there's a bit of curvature at the top and bottom of this waveform. For our calculations, this is one of the assumptions we're going to make, that this is just a perfect square wave, because it makes calculating the area much easier. Then we can just multiply the voltage by the time, and basically just treat this as a rectangle. Now the theory tells us that while we're applying a positive voltage across the inductor, the current's going to increase, and then while the voltage across the inductor is negative, it's going to decrease. So let's have a look at the inductor current and see if that holds up. Ah, it does. What a surprise. We can see that while we've got a constant positive voltage across the inductor current has a constant gradient increasing. And we can link this back to the original equation, V equals L di dt. The yellow is our V, which is constant, the L is our inductance, which is constant, and the blue is our current. Di dt is the rate of change of current, which is also constant. We can see it's constantly increasing. And then when our V goes negative, it's decreasing, always at a constant rate. Now let's see how this current waveform changes as we vary the duty cycle. We can see that at a lower duty cycle, the voltage across the inductor is higher, so the gradient that it rises at is steeper, but then because we've got a lower duty cycle, our output voltage is lower, so the inductor current is going to drop down with a more gentle slope. And because we've got continuous current, it's always going to start and finish at the same point. Speaking of which, let's see what happens if we reduce our output current. We can see that the inductor current drops down and eventually becomes discontinuous. I'm going to turn off the inductor voltage because it's a bit horrible. And here we can see the inductor current is now discontinuous. When the MOSFET's on, the current increases, and then when the MOSFET turns off, the current decreases until it reaches zero. Then the inductor has no stored energy, so it's just going to sit at zero until the MOSFET turns back on. If we swapped our diode for a MOSFET, the current would go negative, because a MOSFET that's turned on can conduct in both directions, whereas a diode blocks the output voltage from flowing back into the inductor, so that's why the current just sits at zero. Something else quite interesting to note is that right now we're at about 50% duty cycle, and if I get it so that we're just discontinuous, you can see hits zero and then comes back up. If I increase or decrease the duty cycle, we actually leave discontinuous mode and never reach zero. And you can see the same happens when I decrease, so there's discontinuous, and we're back to continuous again. That's because the ripple current through the inductor is highest at 50% duty cycle. And we saw that earlier when we looked at how the output voltage changes with duty cycle. Between 20 and 80% duty cycle, our current became discontinuous and our output voltage rose up. But at the two extremes it was continuous. And that's exactly what is happening here. As we want to avoid discontinuous current, the delta I, or peak-to-peak current ripple, should be calculated based on the minimum expected load. In the case of the buck converter, that is very simple, because the inductor is always connected to the output, so the inductor current is the output current. I've designed this converter for a minimum output current of 100 milliamps, so that means we need to make sure that the inductor current is continuous at all currents above 100 milliamps. And the way we're going to do that is by making 100 milliamps our threshold current. That means that when the inductor current is an average of 100 milliamps, the lowest point of the ripple, or the trough, should be at 0 amps, just on the boundary between continuous and discontinuous operation. As the inductor current is a symmetrical wave, that means the peak of the inductor current should be double the average. So as the current goes up and down between 0 and 200 milliamps, it averages 100 milliamps, exactly what we need. I'm designing all three converters to operate at 50% duty cycle to further simplify the maths, but don't worry, it's not really any different for whatever duty cycle you need. We can apply the equation we derived earlier to either of the operating steps, though for a buck converter the second is slightly simpler because the inductor is just connected across the output rather than between the input and output, so let's go with that. In this case we have an output voltage of 5 volts because we have a 10 volt input and a 50% duty cycle. The off time of the PWM is the period multiplied by 1 minus the duty cycle. I want to switch at 50 kHz, so that's a 20-second period, and with a 50% duty cycle we just need to half that to get the off time, so 10 microseconds. Then all we have to do is multiply and divide. We're putting 5 volts across our inductor for 10 microseconds, and we want to divide that by the increase in current of 200 milliamps, and that gives us an inductance of 250 microhenry. How easy was that? Now let's take a look at the other two converters, both of which share the same first step, with the inductor connected across the input. This means the calculations for inductance will be the same. So the voltage across the inductor is the input voltage of our converter, 10 volts, and the time it's across it is the on time, so the period of 20 microseconds multiplied by the duty cycle of a half to give 10 microseconds. Then divide by the current ripple of 200 milliamps to get an inductance of 500 microhenry, which makes sense because we're applying double the voltage that we were with the buck converter, but for the same amount of time, and we want the same current ripple, so we need twice the inductance to slow down the rising of the inductor current. Let's have a quick look at the waveforms of the boost and buck boost converters to see how they differ from the buck converter. So first off, let's look at the boost converter. This is the inductor voltage. When we take the duty cycle high, the negative inductor voltage gets quite large, and that's because the output voltage has that almost exponential increase with duty cycle. If I zoom out a little, it'll become even more clear. This is at a low duty cycle, and you can see the positive voltage across the inductor is always going to be the supply voltage, so 10 volts. We're currently at 10 volts per division. But as I increase the duty cycle, there's 50%, so you can see the area of the positive voltage is 2 squares, so the area of the negative voltage also needs to be 2 squares. But if I now take it to 75% duty cycle, the 3 squares of 10 volts have to be balanced out with 3 squares making up 30 volts here, because we've only got a third of the time for that energy to come back out. Something quite interesting as well is the voltage across the switching devices. So at 50% duty cycle, you can see that when the MOSFET's off, it has to block 20 volts. And that's because we've got a 20 volt output. It's important to remember when picking devices, they usually have to block at the very minimum the highest voltage in the system, and in the case of buck boost, as we'll see shortly, they have to block the input voltage plus the output voltage. And of course that means if we increase the duty cycle, the voltage across the MOSFET gets pretty high. And now here we have the buck boost converter. Once again, this is the inductor voltage, positive 10 as we charge it up, and negative 10 as we take the energy back out. If we increase the duty cycle, just like the boost converter, the negative voltage across the inductor increases because that's our output voltage. Now, as I mentioned earlier, it's probably worth having a look at the voltage across the switching devices. So let's start by looking at the voltage across the MOSFET. I've now got the scope on 10 volts per division, and you can clearly see that when it's off, the MOSFET has 20 volts across it, even though we've got a 10 volt input and a 10 volt output. And as I mentioned when we were looking at the boost converter, that's because the devices in the buck boost converter have to block the difference between input and output. And as the output's negative, that's quite significant, especially when we turn up the duty cycle. Next we need to calculate our capacitances, which we can split into 2 groups: capacitors with continuous current, so ones that are always connected to the inductor, and discontinuous current, so ones that are connected to the switches. Capacitors with discontinuous current are a bit easier to calculate, so we'll start with them. As with the inductor, we can calculate using values from either the first or second steps, but it's a lot easier to go for whichever one doesn't have the capacitor connected to the inductor. The reason for this becomes clear when we look at the waveforms. So once again, here's our PWM signal with a duty cycle of about 50%. Let's now have a look at how the capacitor current relates to that. We can see that when the MOSFET's on, the capacitor current gets increasingly negative, whereas when it's off, it's pretty much constant at this positive level. Just like we did for the inductor voltage, we need to calculate the area under this curve, this time the current rather than voltage. Clearly, it's going to be easier to calculate this area, which is basically just a rectangle, than this area, which is a triangle, and the top of the triangle we don't really know where it is. Although it looks like it's at 0, that's not necessarily the case. The inductor is the cause of this increasing current, so when calculating this capacitance, make sure to think about whether it's the first or second step that has the capacitor disconnected from the inductor. So I'm going to zoom in on this current ripple, and let's have a look at the voltage. Oh, well, it doesn't really look like it's changing at all. That's because the voltage ripple is so much smaller than the voltage itself. So what I'm going to do is AC couple this measurement, which then means we can zoom in and just see the ripple. There we go. So you can see how in the step that we want to use, because there's a constant current flowing into the capacitor voltage increase is linear, whereas down here the capacitor voltage drops and isn't really very straight, which isn't a problem, it just means the calculations are a bit more complicated. Something interesting to note is how the capacitor voltage appears to jump here, and even more so here. This is because of the ESR of the capacitor. So you have to imagine that every capacitor has a resistance in series, and what we're seeing here is the voltage drop across that resistance as the current changes direction. And even though I've used polymer capacitors which have very low ESR, this still has an effect on the ripple. And quite often, this ESR actually contributes more to the ripple voltage on the capacitor than the capacitance itself. So it's something really important to consider. And I've gone into more detail on ESR in my Capacitors for Power Electronics video, linked above. Now what I'm going to do is increase the output current, and as we can see, both the current ripple and therefore the voltage ripple increase. So this means we have to design our capacitors to be able to handle the highest current that we expect for our converter. So the current flowing into or out of our capacitor while it's disconnected from the inductor will be the maximum input or output current of the converter respectively, depending on where the capacitor is located in the circuit. I'm designing all three converters for a power rating of 30 watts, so that means at 10 volts we'll have a maximum 3 amp input current. The time over which the capacitor will be getting charged up by this current is how long the switch is off, which we've already calculated to be 10 microseconds. And I've decided that I want a maximum peak-to-peak voltage ripple of 10 millivolts. So what we want to calculate is the capacitance that will take in 3 amps for 10 microseconds, and it'll only increase in voltage by 10 millivolts. The equation we need is derived from the standard capacitor current equation, I equals C dV dt, and is almost identical to the one we used for the inductance, except the voltage and current swap places. So all we need to do now is put our values into this equation. We're putting into the capacitor 3 amps for 10 microseconds, and we're going to divide by the increase in voltage that we want, 10 millivolts, and this gives us a capacitance of 3 millifarad, or 3000 microfarad. To calculate input and output currents, it's easiest if we just assume 100% efficiency for now, and then we can round up a little bit at the end. A good DC-to-DC converter should be at least 90% efficient, so it's not going to be too far off. As this process is identical for the discontinuous current capacitors in boost and buck boost converters, I'm not going to go over those, but just make sure you're using the right current, so input or output, and the right time, so the portion of the period when the capacitor isn't connected to the inductor. Finally, we have the capacitors lucky enough to be permanently connected to the inductor, the input capacitor of the boost converter and the output capacitor of the buck converter. Why does this make them lucky? Well, it means they don't have to fill in a gap in the current flow like the capacitors we just calculated. All they have to do is smooth out the current ripple of the inductor, which in our case is pretty small. Let's go straight to the waveforms as they make this easier to understand. As a quick reminder, this is the current waveform that the input capacitor has to deal with. It gets charged up while the MOSFET's off and then discharged while the MOSFET's on. Note these rapid changes in current as the MOSFET turns on and off. These become very important once we take a look at the physical design of the converter later on. In contrast, this is the current waveform that the output capacitor has to deal with. We've got this nice, smooth, symmetrical, triangular waveform with no sudden changes in current. And what we're looking at here is the current ripple of the inductor, so all that our output capacitor has to do is fill in these little triangles. Now we've seen that the voltage across the capacitor is determined by the integral of the current going into it. And the integral of a triangle wave is kind of a sine wave. It's not a true sinusoid, but it's fairly close. And crucially, it's got no sudden changes anywhere, it's just nice and smooth. Which is really important when it comes to EMI and just general noise, as this is going to have far less harmonic content than this jiggedy-jaggedy voltage waveform we see at the input. To calculate the capacitance we need with continuous current, we once again need to find the area under this current waveform, which is fairly simple, but it's easier to make a silly mistake, so let's draw out our waveform to make sure we don't forget anything. So the current flowing through our capacitor looks something like this, and it's essentially just the ripple current of our inductor, which of course we know because we defined it, and that's how we chose our inductance. In the case of this converter, that was 200 milliamps. And what we now want to calculate is this area here, or this area here, or this area here. They're all the same. Clearly this is just a case of working out the area of a triangle, but we need to make sure we get the dimensions of the triangle correct. The width is going to be half of a period, irrespective of what our duty cycle is, because this waveform's symmetrical. So my period is 20 microseconds, so half of that is 10 microseconds. Then the height of our triangle is going to be half of the height of the ripple, which is 200 milliamps. So that means the height of the triangle is 100 milliamps. And then of course the area of the triangle is the width times the height divided by 2, because it's half of the full rectangle. So that means we got the period and halved it, and multiplied that by half of the current ripple, and then we halved all of that, which is of course the same as simply multiplying the period by the current ripple and dividing by 8. Once again, all we need to do now is divide this area by the peak-to-peak ripple voltage we want, and boom, we get the capacitance we need. Now there's two things that jump out when calculating this capacitance. First is that it's tiny, 50 microfarads. That's 60 times smaller than the input capacitance. This is mostly because this converter has been designed for a very small current ripple, which means the output capacitor doesn't really have much smoothing to do. A lower inductance would require a larger capacitance. The other thing is that this capacitance isn't affected by the output current of the converter, only the current ripple, so this means that the voltage ripple at the output will be the same for all loads, whereas the input ripple reduces at lighter load. And we can see that here. This is the input voltage ripple as I turn the output current up and down, whereas here's the output voltage ripple, and it doesn't really change much. It gets a little bit bigger with higher load, but nowhere near as much as the input ripple does. So that's how to calculate the values for all the energy storage components in these three converter topologies. There are of course other ratings of these components, like capacitor voltage, and other components like the MOSFET and the diode, which we'll take a look at next. One quick thing I must mention is that most converters in the real world will be designed to operate over a range of voltages, be that input, output or both. If you need your converter to operate over a range of voltages, it's important to consider what duty cycle will lead to the largest ripple current, as sometimes this isn't very intuitive. For example, these are the inductances required for the three converter topologies if we want a 10 volt output and a variable input. Note that while buck and buck boost need the largest inductance at the lowest duty cycle, boost actually requires the largest inductance at 33% duty cycle. Bit weird. I'd recommend writing a quick bit of code or using an online calculator to make sure your converter will meet your spec in the worst case scenario. So now that we know the values for our main components, let's take a look at them one at a time in more detail, starting with the inductor. When selecting an inductor, you'll usually find two different maximum currents on the datasheet. One is the saturation current, so beyond this current, the inductor core can't take any more magnetic flux and the whole thing will stop behaving like an inductor, meaning the current will shoot up. In reality, this doesn't happen at a specific current, more over a range of currents, but what's usually specified is the current that will cause the inductance to drop by 30%, as we can see here. We need to make sure the peaks of our inductor current stay below this value to prevent saturation of the inductor, which will lead to the inductance dropping, which can cause excessive current to flow. The second current specified is the maximum RMS current. This is determined by the inductor's DC resistance as well as its ability to dissipate any heat into the environment. We need to make sure our average current never exceeds this value or our inductor will overheat, but it's okay if the peaks of the ripple exceed it. It's of course a good idea to use a slightly higher inductance than calculated to compensate for this inductance drop at higher currents. Doing that will also reduce the threshold current below which current becomes discontinuous, giving a bit of margin for any non-idealities and component tolerances. On this inductor datasheet we can also see typical and maximum DC resistances, which we can use to calculate voltage drops and losses. Finally, there's also self-resonant frequency, which most of the time we don't need to worry about. This is a result of the parasitic capacitance in the inductor, which, together with the inductance, forms an LC tank with a resonant frequency, in this case 15.2 MHz. As long as this is far above the switching frequency, there's nothing to worry about, but as you get closer to this frequency, the effectiveness of the inductor will reduce as it starts to behave more and more like a capacitor. Speaking of which, what are the other parameters we need to consider for our capacitors, other than of course capacitance? Well, first and foremost we have the maximum rated voltage. We need to make sure that, ideally, the voltage on the capacitor never exceeds this value, as that will significantly reduce the lifetime of the capacitor and can quite easily result in catastrophic failure. You can see this datasheet specifies a surge voltage, but I'd resist the temptation to use this, even for the peaks of the ripple, because of how quickly overvoltage can cause permanent damage. Next we have the leakage current, which is how much current leaks through the capacitor while it's charged up. Usually this is so low that we don't really care about it, but it's important to be aware of and can become more significant at higher temperatures. Finally we have dissipation factor, ripple current and ESR, which are really just three ways of telling us the same thing. ESR is the equivalent series resistance of the capacitor, which I mentioned briefly earlier. This is the parasitic resistance in the capacitor, and it has two important effects. First is that, as we've seen, any current flowing into or out of the capacitor passes through this series resistance, which results in a voltage drop. This is a problem because we're trying to use our capacitor to smooth voltage, but this resistance is adding in some voltage ripple that the capacitor can't do anything about, reducing its effectiveness, especially at high frequencies. The second problem with ESR is that all this current passing through it is causing I2R losses which heat up the capacitor. This is where the ripple current rating has come from. It's the maximum current that we can put in and out of our capacitor before it overheats from these I2R losses. Dissipation factor is basically just another way of stating ESR, but it takes into account capacitance, meaning you can use it to compare small and large capacitors, where the ESR would be influenced more by their size than their quality, because big capacitors just inherently have lower ESR. Next up is our MOSFET, which has way too many parameters to go over in this video, but luckily I've already made a video all about them, so give that a watch if you want more deets. For now, I'm just going to quickly go over a few key parameters. First of all, we have the maximum drain source voltage. This is the highest voltage our MOSFET can block when it's turned off, and we usually want quite a bit of margin with this, because we get voltage spikes when we turn on and off that'll be quite a bit higher than the voltage the MOSFET has to block in steady state. Next is the maximum continuous drain current, which is how much current can pass through the MOSFET when it's on. We have to be careful with this because there are quite a few things to consider. When a MOSFET's on, it behaves a bit like a resistor. As current flows, there is a voltage drop and some I2R losses. These losses will heat up the MOSFET. How much current one can handle is determined by how well we can get that heat out the MOSFET. If it's just sitting there with no heatsink or active cooling, the max current will be much lower than if it has a big heatsink with a fan on to draw the heat away. So in reality, we need to work out the maximum current of the MOSFET in our specific application by considering its electrical and thermal resistances. Last up is the diode, which is quite similar to the MOSFET. It has a maximum voltage it can block when it's reverse biased, and a maximum current it can conduct when it's forward biased. Once again, this current rating depends on how well cooled the diode is. Unlike a MOSFET, which has a constant on resistance when it's on, a diode has a constant voltage drop, but we can use this to calculate the losses in the same way. We can also see the reverse current or leakage current. Just like the capacitor, this is current that flows when it shouldn't, and it increases a lot with temperature. We actually have exactly the same thing in MOSFETs because they contain diodes. So now that we've got our components, we need to put them all together. There's a number of things that influence how we choose to arrange them, but the two main ones are electrical and thermal performance. Thermal performance is quite simple. Basically, can we keep our hot components cool? Usually the MOSFET and diode, and sometimes also the inductor. I'm not going to go into that in this video, but let me know if you'd like to see a video on the common compromise that needs to be made between good cooling and good electrical layout, as usually they're not the same. What do I mean by a good electrical layout? If we have all the right components on our circuit board joined up correctly, surely it's just going to work. Oh, if only. Layout is really important in power electronics and can make or break a design. This is because of the rapid changes in both voltage and current caused by the switching. I have here the schematics for all three converters, and what I've done is coloured the connections between components based on whether they have rapid changes in voltage, current, or both. When voltage changes very quickly, known as high dVdt, it can result in current flow in unexpected places, because of small capacitances between traces and components. The current is determined by the equation I equals C dVdt. And because the current is the product of capacitance and dVdt, even a small capacitance can carry a significant current if the voltage across it changes fast enough. These currents can wreak havoc in analog circuitry and can even upset digital microcontrollers, so it's important to keep them to a minimum. To do this, we just need to keep any parts of the circuit with high dVdt away from the rest of the circuit. Nothing crazy, just enough that there isn't a significant capacitance formed. Usually this is as simple as just not putting anything on the layers of the PCB above or below an area of high dVdt, because adjacent layers of a PCB are close enough together that there can be a decent capacitance between them. The other thing that changes very quickly is current, dIdt, and in my opinion this is much more significant. Why is that? Well, let's take a look at an equation that contains dIdt, the good old inductor voltage equation, V equals L dIdt. This tells us that if we have current flowing through an inductance and then we suddenly change that current, we'll get a voltage across the inductance. This is a big problem because every wire, every component leg, and every copper trace has an inductance. They're everywhere, and there's nothing we can do to completely eliminate them. This inductance is the cause of the voltage spikes across the MOSFET I mentioned earlier that mean we have to use a device rated for much higher voltage than we should ideally need. If we can reduce this inductance, we can actually improve the efficiency of the converter by either using a lower voltage and therefore lower resistance MOSFET, or by switching the same MOSFET faster, which will reduce our switching losses. To minimise the inductance, what we need to do is minimise the distance between components. see how close together I have the MOSFET, diode and capacitors on this boost converter, keeping what is known as the loop area, the area of the shape drawn out by the current path, as small as possible, as this directly correlates to the inductance. The components that experience high dIdt should be the first to be placed in the design, as close together as possible, making sure to consider cooling and also whether you can actually assemble it. It's quite easy to get carried away and place your components 0.1mm apart, and then feel a bit stupid when you come to solder it. Components that don't experience high dIdt can be placed later, as any inductance in the path connecting these isn't really a problem, so their location's less critical. We can see that there's a bit of a problem with the buck boost converter. Every single component except the inductor sees high dIdt. This is yet another drawback with this topology and makes optimizing layout more challenging than for the other two converters. There's many ways to work out where in the circuit we'll see fast changing voltage or current, but there are a few easy points worth remembering. First of all, an inductor will never have high dIdt through it, because its inductance is so high it won't allow it. Remember, we use inductors to smooth current, so their job is to prevent fast changes. The same is true for capacitors and DVDT. Their whole job is to prevent the voltage changing rapidly. In hard-switched converters like these, the switching node, so where the MOSFET and diode are joined, will always see both high dIdt and high DVDT as the current swaps between flowing through the MOSFET and flowing through the diode, while the voltage is alternately clamped by whichever switch is turned on. I currently have a video in the works all about how component placement and board layout can affect efficiency, so make sure to subscribe to see that when it comes out. Now for the final part of this video, let's try to validate some of the design requirements we originally laid out for our converter, starting with the voltage ripple. At 30 watts we should hopefully see 10 mV peak-to-peak ripple at both input and output, so let's check them. So first off, here's our input voltage ripple. You can see I've got the scope to measure for us. Peak-to-peak voltage ripple, 100 mV. What happened to the 10 mV we designed for? Well, there's two different things contributing to this ripple, and I alluded to them before. We've got the ripple from the capacitance, which is the slopey part at the top and the bottom, and then we've got the ripple from the ESR, which is the sharp changing ripple. Now if we take a closer look at just the slopey ripple, you'll see that this slope increases by 2 divisions, and we're at 5 mV per division. So there's our 10 mV. And if we had 0 ESR, then this steep part of the ripple wouldn't be here, and it would just go up 10 mV and then down 10 mV, up and down. So clearly we've got exactly the right capacitance, which makes sense because this board does indeed have exactly 3000 microfarads of input capacitance. But of course the ripple isn't 10 mV, it's 100 mV. That extra 90 mV is all just down to the ESR. So now let's have a look at the output. Now this is a lot closer to what we want. If I zoom in, we can see the scope's reading 27 mV peak to peak. And the reason this is so much better is that, firstly, I've used a ceramic capacitor for the output, and these have very low ESR. And secondly, if you remember back to when we were calculating the values, the output capacitor doesn't have much current flowing through it, so even at the same ESR, there'd be less voltage drop across it. So that means we've got the compounding benefit of lower ESR and lower current through the ESR. However, we're clearly still a bit of a way off the 10 mV we designed for. And another reason for this is that ceramic capacitors, particularly modern ones, have lower capacitance at higher voltage. So even though the capacitor I'm using says it's 47 microfarads, once it's charged up to its rated voltage, the capacitance might be only 20 microfarads, hence the larger ripple. Now the reason for this is all to do with the dielectrics they use. Different dielectrics have different levels of capacitance loss, and it's something I'm hoping to do a video about at some point, but just be wary of that, and maybe check out the performance of the dielectric used in the capacitors you're looking at before you buy them. Next, let's take a look at efficiency. To approximate the overall efficiency of the converter, we'd need to consider an awful lot of things, such as the DC resistance of the inductor and the switching losses of the MOSFET. But as a quick example of how we'd go about calculating losses in components and how insightful doing so can be, let's take a look at the losses in our diode. When we run the buck converter at 30 watts, we're going to get a 6 amp output current for our 5 volt output voltage. As we're running at a 50% duty cycle, that 6 amps is going to be flowing through the diode for half the time, and through the MOSFET the rest of the time. If we take a look at the datasheet, we can see how the forward voltage changes with current, and also temperature. This makes things a bit tricky because the MOSFET will heat up from the current, so we don't actually know how hot it is. But for now, let's pretend it doesn't, and assume it's at 25 degrees. We can see that at a current of 6 amps we'll have a forward voltage of about 0.43 volts. Multiplying this by the current gives a power of 2.58 watts. Though of course we only have this power in the diode while current's flowing through it, so we can half it to get the average power because of our 50% duty cycle. That gives us 1.29 watts of loss in the diode. Great, but how can we validate this? Well, I think it would be quite fun for us to try a little calorimetry, using the temperature increase of a component to work out how much power it's dissipating. The insulated TO220 package of this diode has a thermal resistance from junction to ambient of 62.5 degrees per watt, so in theory that means the junction at the heart of the diode will be 80.6 degrees hotter than the ambient temperature. But we can't see the junction, so how hot will the case get, the bit we can see? Well, to work that out we can use the other thermal resistance in the datasheet, junction to case, to work out the difference between the case and the junction. That's 4.2 degrees per watt, so the case should be 5.4 degrees cooler than the junction, and therefore about 76 degrees hotter than ambient. Conveniently, I've just bought a nice thermal camera, so let's take a look at our converter and see how hot our diode really gets. Right, so here we've got the thermal camera looking at the buck converter. I've added 2 measurement points. The first is just looking at the bench to get ambient temperature, and the second is fixed on the case of our diode. You can see right now there's an ambient temperature of about 19 degrees, which is pretty toasty. I decided to treat myself to some heating this weekend. Now let's turn on the 30 watt load and see how hot our diode gets. As expected, it's by far the hottest component, but we can also see the inductor heating up a bit, which makes sense because this inductor is technically only rated for 5.8 amps. But the rating on the datasheet tends to be for a high ambient temperature, so I think this will be fine in my 20 degree lab. We're now up to a 51 degree delta between ambient and the diode case. It looks like it's still got a little bit to go, so I'm going to leave it for now. Right, it's now been 12 minutes and it looks like we've pretty much thermally saturated the whole converter. Our diode temperature's a bit over 77 degrees, so about 57 degrees above ambient. Now of course that's a lot less than the over 80 degrees that we expected, but remember we made the assumption that our diode is at just 25 degrees. If we redo those calculations using the forward voltage we'd get with a junction temperature of 80 degrees, you can see the delta we expect drops to just 61 degrees. And just while I've been talking, we've gained another 1.5 degrees, putting our delta at 59 degrees. So I think if we left this for long enough, we would indeed be at that 61 degrees we've calculated. How cool is that? Obviously you can do the maths we've done in reverse to calculate how much power is being lost in a component when you don't really know as much about what's going on internally. For example, if the datasheet doesn't give such a helpful plot of forward voltage. I've now turned the load off, and this presents the opportunity to do further thermal analysis of the circuit, looking at how quickly different components cool down. For example, we can now see that our inductor is actually hotter than our diode. That's because the inductor has a lot more thermal mass in its core, so it takes longer to cool back down. Using clever maths, you can analyse how quickly components cool down to work out their thermal mass, which will tell you how they'll respond to transients. For example, the diode has cooled down quite quickly, so that means if we put a short pulse of current through that, it'll heat up quite quickly, whereas the inductor clearly has a lot of thermal mass, so that means we can put a brief pulse of higher current through that, and it won't heat up as much, because anything that takes longer to cool down will also take longer to heat up. So that's it. Hopefully this video's been helpful for anyone looking to design a DC to DC converter, or just pass an exam. And on that sorry note, thank you very much for watching. Goodbye. Wow, I have bad circulation.